Okay. So,
Okay, cool.
all right. So yeah, this podcast is going to be about the ADC, the attitude determination and control subsystem, and I'm the future ADCS engineer for this mission. So my name's Manav, and yeah, same person as last time. Uh,
I'm Francesca. I'm the Deputy Chief Engineer.
I'm Spencer. I'm the Deputy Systems Integration Lead.
right. So yeah, I'll start with a quick overview of the ADCS, and then the main components, the main softwares and algorithms used, and then we'll get into the questions. So an ADCS has the job of determining the attitude, that is the orientation of the spacecraft, and then controlling it to point in a desired direction. Not every mission has, pointing requirements, but most spacecraft do at least have determination requirements, and anything related to controlling or pointing of instruments or radios or communication tools or whatever requires some form of control to reject the disturbances that are out there in space and point the spacecraft to a desired attitude. So to accomplish this, the ADCS has several components. So the first main component are the reaction wheels. So the reaction wheels are usually three wheels oriented along three perpendicular axes, and usually they have one extra one for redundancy, but three is the norm for small satellites. Four is for missions that there's a heavy emphasis on the ADCS, and it's not allowed to be a failure point, such as our mission. Um, the reaction wheels work based on Newton's second law of motion, but for rotating bodies. So when you spin one reaction wheel faster in one direction, the rest of the spacecraft will feel an equal and opposite torque. And by controlling the speed of the reaction wheel, you can control the angular velocity of the spacecraft. And by tuning that and controlling it using like a feedback loop, you can control the attitude of the spacecraft. This Okay, yeah, so on the screen, this is the redundant wheel. So you have one in the X, Y, and Z, and then you have one that's pointing in all three. Normally, if you're using four, this is not the desired, like not the optimal configuration, but it is a configuration. Um, so for the reaction wheels, usually it's good for three-axis control. If you have three wheels, you can rotate all three at different speeds and get them to any attitude that's possible. And their accuracy can be pretty good. Usually, at less than 1 degree is normal. However, this does require electricity and a controller, and because it's a mechanical system, there is a spinning wheel. It is prone to mechanical failure if you spin it too fast. Because of this, the reaction because of this, the reaction wheel has a maximum speed, which is called the saturation speed, and this is usually given in RPM. I don't know what the actual RPM values are, but they're usually in like the couple thousand of RPMs. Yeah. So that's the reaction wheels. This is the option used for most small sats, and this is also the one that will be used on our spacecraft. Um, but there are a couple others that I'm going to go over just so we can get like a good idea of the benefits and drawbacks of each thing.
Is the main reason that we're not using four reaction wheels just for monetary reasons, like the
Uh,
price?
yeah, that would be the only real reason. We would want four reaction wheels because, in case one fails, it's nice to have redundancy, right? If you have four wheels and one fails, you still have all three axes within reach.
Okay.
Yeah. I guess if you want to frame this as a linear algebra problem, in 2 dimensions, it's pretty easy. If these three vectors are your basis vectors, and then this is like some other vector A, even if x or y is gone, you can still map out like any other vector using a linear combination of these two. So if you think of these axes as, okay, this is the axes about which you can rotate, then, for a three-dimensional system, if you lose one reaction wheel, in this case the y, as long as the a reaction wheel is not perfectly, parallel with these two, you'll still be able to rotate in any axes that you want. Um,
Okay.
yeah. So the reaction wheels are the first system. The second one is called gas thrusters. So these work based completely on Newton's second law. Usually they come in pairs. I'm not going to draw all of them because it's a pain, but usually you'll have two, like a pair of thrusters, and when you fire And they call it cold gas because there's a canister of gas and it's piped up to all of these, and using a valve that's controlled by the control system, you can turn on the like you can let the gas out, and when the gas escapes, it has some momentum that it carries away, and your spacecraft will spin with the opposite momentum. Usually, there's more problems with these because if your reaction wheels aren't aligned perfectly, right? So in this case, let's say there's like a small deviation, this will actually end up causing another torque. So like this right here is this little red over here is the deviation. So what will actually end up happening is if you fired both of these together, there would actually be like a small moment. So this one would have gas flying this way. This one would have gas flying this way. There'd be a net torque in that direction, right? So with thrusters, usually that's something that you have to think about is the error in the design of the mechanical, like the mechanical tolerance, you could say. These also have very good accuracy, usually on the order of like 1 degree, but the control algorithms that have to be developed have to be much more, I'd say, tuned and better, and you have to account for the error much more carefully. A major drawback to these is actually the finite amount of gas that you have, because you can only expend this momentum while you have gas, right? In this case, we're using Newton's second law in this form, where the force is equal to the change in momentum, and in this case, the change in momentum is mv dot, or oops, the change in the time derivative of mass times volume, but what we really care about is this m dot plus mv dot. And for a cold gas thruster, usually this term is zero. You're not really changing the velocity of the gas. What you're doing is you're expelling mass out the back, and that's what causes your thing. But every time you do it, you lose a little bit of mass. Your matrix, your inertia matrix does change a very small amount. Usually it's negligible, but it does change. And once you've exhausted all your mass, you no longer have this term, so you no longer have control. And that's a limitation on cold gas thrusters. Yeah. One other thing is that, something I forgot to mention. Usually this gas is stored at a high pressure, and it has to be cooled. Cold gas, emphasis on cold. And gas, you want to maximize the, its ability to last a long time, you have to put it under high pressure so you can store a large amount of gas and also get the high velocity jets. So yeah, that's cold gas thrusters. We will not be using these because they are a pain, but and we don't have the experience to do it. But it is an option, and it is good to know. The next one is a magnetorquer. So a magnetorquer is a simple device. It's just a solenoid, and you decide how much current is going through it. So you apply some voltage. It has some resistance, usually small, and because of that, there will be some current that goes through it. This current will generate a magnetic field, which goes like this. And this is especially good for the control that you get is very small, but it is not zero. So if you have a very like loose pointing requirement, it's just you need to point straight north or straight south or some variation of only in one direction, then this can suffice. You might be wondering, where does this how is this used if you just have a magnetic field? Well, it actually uses the I drew these arrows wrong. You usually end up using the Earth's magnetic field, because if the Earth's magnetic field cuts this way, these two will actually try to align exactly how a compass would, and that would generate a torque. So this would actually end up putting a torque this way to try and rotate itself to align with the Earth's magnetic field, or the other way. I forget the exact convention. Yeah, it's a passive system. There's no it's usually a passive system. You're just aligning yourself with a direction. You're not really trying to point yourself anywhere. It's just we only really need to point exactly that way or exactly this way, and that's what it goes off of. So yeah, that's it for the major actuators, that at least the ones that we care about for satellites. So now we're going to go into the attitude determination part. So
real quick before that, just while we're on the topic of the magnetorquers,
mhm.
I think I mentioned it in the last podcast when I think we talked about detumble a little bit.
Yeah.
And I want to bring it up again now. So for our mission, are we using the magnet torquers to try to stabilize our CubeSat during detumble?
Yes. So you okay? Yeah. So you jumped a little ahead. I was gonna mention this later, but that's fine. So one thing that happens with magnet torquers is the faster you're spinning, the the more you'll notice its effect. So I guess here's here's how I would draw it out to someone. Let's say you have, you know, a small magnet, right? And let's say this is north, this is south, and this is south, this is north. I'm gonna stop drawing these arrows because it's not useful, and I keep forgetting the convention. But to have this north align with this south, it will only have a torque that's proportional to this angle, right? It's not gonna have much. However, if this thing was spinning like crazy, then every time you spin, I guess here, I'll do it like this. When you're in this position, you'll have the maximum amount of torque, right? Because you're at a 90-degree angle, it's pulling this here and this here. So that's the maximum torque. Versus if you're completely aligned, say north here, south here, there is no torque here. The reason you would continue spinning is because of your inertia, not really your torque. And then when you're the other way, right, when you are, say something like north here, south here, then your torque is, again, limited by this angle theta. So as you're spinning, the magnet torque will slowly, I guess decay is the right way, is the way I would describe it at least, is it will slowly decay your angular velocity up until it's slow enough that your reaction wheels can take over. Because, when you're, the reason it's called detumble is because you're spinning uncontrollably. So, you turn on your magnet torquers, you let them slowly bring down your angular velocity up until your reaction wheels are able to control it and compensate for the errors. Right?
Okay.
Yeah.
So do the magnet torquers only have the most profound effect during detumble?
Um.
And what I'm getting at?
Yeah. Normally they're just used in detumble. I don't think. I think okay. So there are papers out there that say it's possible to use it as like a reaction wheel system where it can point in all three directions. But I don't think I've seen a mission do that yet. Or if I have, it's only in the experimental phase, not really it's a trusted idea. But yeah, it's usually used in detumble, and it's also used for when your pointing requirements aren't very strong, right? If you need to point exactly north, you can just put a magnet torquer that says, okay, this magnet torquer will have 0 torque when it's pointing exactly north, and then just leave it on constantly. And your spacecraft will almost always be pointing north with a bit of error, but if you don't have a pointing requirement, then that's fine.
Makes sense.
Mm-hmm.
Is SPICEsat's ADCS going to have 3 magnet torquers?
Blue Canyon hasn't gotten back to us, so
Okay, that's fair. That's fair.
yeah,
So the number of magnet torquers that you would like to have?
This is
Or is that according to the pointing budget that you'll get it to?
the magnet torquers won't have anything to do with the pointing budget. We don't really,
Really?
yeah, we don't use magnet torquers to do point. We're not going to use it. It's a possibility. We're not doing it though. It's an area of research on its own to see if that works and then to what extent and what are the benefits and cons. The cons would be you have to run magnet torquers constantly, and magnet torquers are just wires, right? You're just running a ton. You're just making a magnetic field. What its effects are on the electronics inside. If you have very sensitive equipment, like a large magnetic field will mess something up. How reliable are they? What are the errors? How accurate can you be? What is the maximum torque you can generate? All of those are questions that, I know they're out there and there's people working on them, but I don't have the exact answer.
Okay. More applicable to ours, I guess. I would assume that for us, since we're only really using it for detumble, we'd only want one, right? Or we'd only need one.
Yeah.
At
So,
least.
yeah, we would only really need one. I guess it would be nice to have redundancy if possible because so one of the other uses of a magnet torquer is as a magnetometer. So the same phenomenon. So I guess this is like a little bit of electromagnetism, but the same way how if you put a magnet in a, or sorry, no, if you have two magnets or two magnetic fields. They'll try to align each other, right?
Mhm.
But if you have a magnetic field and a rotating wire, or like a rotating coil, it'll generate a little bit of EMF, and that EMF is detectable. So a magnetorquer, in theory, could be used to detect magnetic fields. Not saying it will, but it's possible. And it really depends on what Blue Canyon sells us, right? If they hand us an ADCS with, you know, 3 magnetorquers inside, like, great, we have 3 magnetorquers. I think it's gonna have 1 or 2. I don't actually know because they don't tell us anything. And this is an old paper. So yeah, MEMS mag. This is a magnetic field. Yeah, they say torque rod's 3, so I would imagine there's 3, but I don't know if this document has changed at all. If Blue Canyon's watching this, I hope they get back to us. We're Rutgers University, please.
You should send this to Blue Canyon.
Yeah, yeah, and have them ghost us forever. Nah, it's whatever. Well, we're happening. It's happening. We're making progress. We'll get there eventually. So yeah. Oh, one major benefit of magnetorquers is that there's no moving parts. So in a cold gas thruster, you have to open a valve. That's a moving part. In a reaction wheel, there's a literal spinning wheel. That's a moving part. All of those are sources of error. A magnetorquer has no moving parts. It's just a coil of wire with electricity running through it. So it's a lot more reliable, you could say, in the face of like mechanical fatigue or anything. Or rather, it's fairly easy to design around it. So yeah, that's the magnetorquer. So the next thing is the attitude determination stuff. So the first thing is the star tracker. So this is the main way of, you know, figuring out where you are. To put it simply, you have a camera, and within that camera is a database of every star in the sky that is bright enough to be detected by the camera. Or usually less, but you get the idea. And what they do is they'll actually look, like this camera will look out into the depths of space, figure out what the stars are, what their angles are with respect to each other, and then after identifying which stars are which, it'll be able to tell you exactly where you are pointing, you know, this camera. I don't know if I need to explain how that works.
No, I don't think you do. I mean,
It's a complicated system. I will say
it's
that.
a complicated system, but I understand what it does and what it gives us, so I
Yeah,
don't think there's really much to explain.
yeah,
It's cool though how it does
It's
that.
really cool that
Yeah,
it
it's
can
cool.
do that.
yeah. I guess I'll go a little into detail because I do think it is cool.
Yes, please go on.
So inside of here, there's a star catalog, and that star catalog has all the brightest stars in the sky. More importantly, it has all the stars that we, or like, okay, so it has the brightest stars, but it also has their, I don't want to say exact, but very, very precise location in the sky, right? So, you know, in the olden days of celestial navigation, and by that I mean like sailors, the way to navigate with those, like the way they navigated was by looking at the stars and by knowing, and like, you know, by looking at what the stars are and what the, you know, what the season is and what the time is, you could accurately tell exactly where you were on Earth because you knew exactly where on the globe you should be to see the stars that you're seeing right now. And so if we change the frame of reference from, oh, the Earth to a satellite, the same exact principle. You look at the stars, you know which one, you know where they are, you know what time it is. You just need to connect, and you know which way the camera is pointing. So you just need to connect a few dots to figure it out. It is amazing though because there's a whole star catalog. Like there's literally just a massive list of stars inside of this device, and it compares it it compares it fast enough to do it 1 time per second, or one at like 1 or 2 hertz. So, yeah, and I think for most star trackers, I think it's like a norm where like you can do dead reckoning. So if you turn on the star tracker, it'll take I think like up to like it's usually like less than 10 seconds to figure out exactly where you're pointing. Because it like once it knows where it is, then it's not really a matter of finding itself from scratch. It's more like I'm just gonna make little updates to, you know, like I already know I'm pointing in this direction. I tilt, a few degrees. I just need to search in that general area of like the night sky. Yeah. So that's star trackers. Now, the accuracy of these things is crazy. It's usually like less than 0.1 of a degree. When you start talking about fractions of a degree, you start using arc seconds and arc minutes. So if you have 1 degree, that's 60 arc minutes. And 1 arc minute is 60 arc seconds. So 0.1 degrees is 360 arc seconds. And arc seconds is usually what the accuracies are given in.
So the higher the arc second, the greater the accuracy.
Wrong way, other way. So.
Oh, whoops. I feel so dumb. Someone edit that out.
No, no, it's fine.
Oh my god.
Yeah.
It's funny. I actually just looked up what an arc second was before this podcast, just out of curiosity.
Someone please edit that out.
No,
I
it's
didn't
fine.
say any.
It's
Yeah, I
fine.
got you. I got you.
It's fine. It's okay. We welcome mistakes.
So the lower the amount of arc seconds.
No,
So
open the door.
no, not now. I'm in a podcast.
Guys,
Oh.
he's-
I got your charger.
I don't need it right now.
Oh
Should we
my
get out of here? I'm recording.
Wait, who's this for?
This is for YouTube. Wait, should we get out of here? Okay. I can't do this right now.
Okay, so the lower amount of arc seconds, the greater the accuracy.
Yes.
Okay.
The lower the arc seconds, the greater the accuracy. Think of it like precision, right? So if you're like, let's say I ask you to look at, let's say I ask you, okay, how accurately are you pointing north? Could you answer that to like with like an amount of error? Like if I said, okay, look north. Obviously, you're not looking dead north, right?
Yeah.
There's going to be some error. If you have your phone, you'll be like, oh, it's like 1 degree off, 2 degrees off, right? If you have the compass app on your phone. The lower the uncertainty, the finer the resolution, the smaller that angle is. Right, that angle of error, basically. I hope that makes sense. Yeah.
No, that makes sense.
One thing to note though, even though these things work pretty fast, which is like 1 to 2 hertz, well, I consider it fast. They're not as fast as like a control algorithm is. So
No, 1 to 2 hertz doesn't seem that fast compared to how fast, what's it called? The control algorithm for our experiments is.
yeah,
Like how fast it's supposed to be.
yeah. Usually the star trackers are at like, usually it's less than 10 hertz, so I'll just use 10 hertz. The control algorithm on like the computer, that thing's usually running at like at least 100 hertz. Like, I would say 100 hertz is like a fair estimate. Usually it's less, or sorry, usually it's faster, but could be slower, could be faster, depending on the application. So the way we get around that is by using what are called motion sensors. And I know, Fran, you have experience with this because of the payload team or like the research side that you're working on. But here's how I will describe the use of star trackers and motion sensors. So your star tracker gives you like a super accurate attitude, but your control algorithm needs to run much faster, right? So let's say this is like a 1 second interval. Or not one, let's just say this thing runs at 1 hertz. And that means, you need to know, but in between these two, right? You need to run your control algorithm at, let's say, 100 hertz. That means you still need like 100 pieces of data, right? And you can't just draw like a horizontal line here. That's pretty inaccurate if you're trying to get, a very fine measurement. So what we do is we have a IMU, an inertial measurement unit, which all it does is give you the angular acceleration and the, I guess, linear acceleration as well, right? And then using the integrals, right, the lovely relationship of w is equal to the integral of a t dt from t0 to t1, and then integrating with position again. So we do theta is equal to the integral t0 to t1 wt dt. This isn't a raw sense. Like, this is like mathematically what's happening. We can kind of try to keep it more accurate. or like we can interpolate between these two, right? Because this will give us a value for how the angle is changing over time, right? This omega, and so we can just apply it here. And usually it'll be like a cone where we're like, okay, the cone is slowly getting wider, and then the star tracker like zips it back down, right? Because IMUs usually are filled with like, I guess, noise and bias, right? You've heard of gyro drift, and yeah, that's a thing where the gyro just slowly drifts away. So what we do is we say, okay, we're definitely in this range, and this accuracy is usually better than just using the IMU, because if you just use the IMU, this thing will just continue drifting away. And then we'll get to this later, but if you use like a filter, then you can actually be pretty. You can bound this even more on each one. So yeah, that's IMUs. Oh, IMUs run very fast. You can run them at like 100 hertz, and it'll mostly work. Not that you should, but you could. And I know like the faster you want to run it, the more error there's going to be. And so you have to be more careful with the algorithms that you use, or rather, you have to spend time tuning it to get to be able to account for the error.
You mean inertial measurement unit, right?
Yeah, IMU's inertial measurement unit.
Okay, just making sure.
All good.
And that's is that the motion sensor?
Yes, motion sensor is a different way of saying it. I say IMU just because that's what's written on like the thing on like the shops when they sell it.
Is it the fancy term for it?
Yeah. The 3-letter acronym.
Okay.
But yeah.
So basically, what you're telling me is that without this IMU, our star tracker would not have it would have more of these like blue lines that are kind of diverging. If this is that what you're trying to get at?
Not quite. So the star tracker is accurate, but it runs slowly, right?
Okay.
So, I guess think about this time between 1 and 2 seconds. According to the star tracker, it's still pointing in the same direction. And then all of a sudden, at 2 seconds, it'll jump down to the next value.
I see. Because it's so slow, which is why we have
Yes.
the IMU in order to make it more slanted.
Yeah. The IMU will give you data that's like, okay, you're heading in kind of like... So the IMU gives you like a general direction, like, oh, you're kind of heading in like this general direction. And then if using some filtering, which we'll get into in just a second, you can actually narrow this pretty well and be like, okay, I am precisely in this general area.
And it does that through that mathematical equation you solved up top.
Version of it. This is
Alright, I'll take your word for it.
Yeah.
Similar idea.
Yeah, similar idea. Usually, in most applications, there's no... Like, taking an integral is usually not the smartest of ideas, right? Because, as you know, there's like
the
constant term, right? The constant term is error, basically. Or not error, but it usually ends up being error, right? Because of that, it's not wise to just blindly take integrals everywhere. We'll get into this in just a second. Actually, let's just get into it. I don't know why.
So are you moving on to the next topic?
Yeah, I'll just move on to the filtering algorithm.
All right. The questions I have can honestly wait till later, so I'll just save them.
Okay. Yeah, that's fine. So the filtering algorithm is how do you filter the data properly? So, normally when you get data that's, I guess, of any kind, it'll never look like a straight line. It'll always look something like this, It'll always just jump around like crazy. The purpose of a filtering algorithm is, okay, how can we extract the data that is most, how can we use this to estimate something, even amidst all the noise that's being measured, right? So, I guess this blue, this dark blue here, is like the measured output. This purple is what the estimate would be. The actual value would actually, it might, spike a little or, fall off, but it would be relatively close. And so the filtering algorithm is what does this, right? Usually there's only a handful of them. There's the least squares approximation, which I'm learning now. This is just a generic algorithm for, okay, if I have a bunch of data, how can I draw a smooth line through it using some amount of basis functions? It's just a curve fitter of sorts. And this is used when you just need to draw a line, right? The next one is optimal estimation. So this is based on optimal, I would assume its roots are, very similar, if not the same, as optimal control theory. But the idea is, what is the most optimal way of using this data to give me what I want? And the most common algorithm is the Kalman filter. So the Kalman filter is generally used when you have like two different sensors. In this case, your star tracker is one of them, and your IMU is the other. That's the wrong color. And your IMU is the other. So the way the Kalman filter works, at the highest intuitive sense, is I have one sensor, the star tracker, which is low speed but high accuracy. And then I have the IMU, which is high speed, but then I guess I don't want to say low accuracy, but I would say like medium accuracy. And so what the Kalman filter does is it poses it as a question, as like a mathematical question, which is, what is the most optimal way to combine this data to give me one number, which is supposed to be, I guess, optimal. How can I combine the data from both of these? Like, how can I fuse the data from both of these to give me an optimal estimate? And I don't have the ability to explain it right now. Matter of fact, I'm learning it this semester later on. But
Pretty cool.
yeah, that's the question it asks. That is the question that is answered.
Mm-hmm.
The answer is usually, okay, you'll get some value, like, okay, you'll get some coefficient value. Usually it's like some alpha. And that tells you, okay, if I have, data 1 and data 2 from the star tracker and IMU respectively, how should I weigh this data? Usually it's like 1 minus alpha times alpha. And that'll give me my estimate of, this is transposed because you do this times this, yeah. And then that'll give you some estimate, usually it's half of that. And this is the value that you use. If there's someone watching this that understands how Kalman filters work, they're probably raging at me because I don't actually know how it works. I know what it is, I know how it works very high level, but I don't actually know how it works yet.
To be fair,
Well-
we don't know how it works either.
As long as Blue Canyon knows how it works, that's what really matters.
Yeah. Actually, I'm pretty sure that's one of Blue Canyon's, like, major... Like, that's one of the reasons why the Blue Canyon ADCS is so accurate, is because... Because they're the ones that they like design the system, they know what all the errors are, they know what all the uncertainties are, or at least they've like placed bounds on them, and because of that, they're able to. They know because they know what the errors are to a really high extent, they're able to design an optimal Kalman filter that does that job very well, right? Because what it comes down to in a Kalman filter is how well can you quantify the uncertainty, right? That's usually a very hard question. You're basically asking, how do we bound, or how do we measure this uncertainty, and then how do we use that number to, find the optimal control, or not the control, the optimal value out of the data that we're collecting. But yeah, Blue Canyon does that very well, which is why they have a computer inside their ADCS. Yeah. And then also on top of the Kalman filter, there's extensions. I think there's like, there's the extended Kalman filter, the unscented Kalman filter, a bunch of other ones. I don't know how any of them work, but that's what I'm gonna have to be learning very soon.
I mean, we're just using whatever Blue Canyon has, yeah.
More or less. More or less.
Oh boy.
We'll put our trust in Blue Canyon.
We'll definitely like try to like, at least I will try to.
It'd be cool to understand it. Like the minute you learn it, you should have a little mini podcast. Be like, guys, I figured it out.
They would probably get very upset if I broke the NDA. But
I forgot about that. Wait, yeah.
yeah, I won't do that. But there's nothing wrong with trying to test our own filters, right? On their ADCS computer, they have their own algorithms running. There's nothing that says we can't try to run our own. And honestly, that's something that, I think Mike's not looking at that right now because he has to do
Well,
his...
it's not top priority.
Yeah, it's not the highest of priorities, but it is up there. And matter of fact, when I transition to ADCS engineer, that is one of the things I will be doing is, studying the the optimal estimation of attitude and attitude determination and control and all of that fun stuff.
So you want to compare, what is it, Blue Canyon's whole filter algorithm to one that you could possibly create and see which one's more accurate? Is that what you
So
want to end up doing?
so here, so okay, so this is where it's like it's an open-ended question, right? So
Yeah.
the Blue Canyon filter is without a doubt like it is designed for that ADCS. However, the important thing is it's you have to measure what the uncertainties are, right? You have to know what the errors are and what their bounds are and what their distributions are. Because our mission has a literal tank of fluid inside, which is by definition extremely uncertain, there is a chance that the Blue Canyon algorithms may not be the most optimal solutions because it's a fluid tank, right? There is no way their ADCS can account for a fluid, right? It does not have the computational power to model a fluid in space, right? They definitely have thought about it, right? I mean, it's not uncommon to have fluids in space, but because like a part of our research is to develop those algorithms, right? And in addition to the control algorithm, right? In addition to the pointing algorithm, there is also the attitude determination algorithm, right? There's two separate algorithms, and they have to work together. Um, Mike is obviously focusing a lot more on the the pointing, right? But it's not it's not like we can neglect the determination, right? We do need to know where we're pointing, and there is a very uncertain disturbance running around in our satellite. So it's an open-ended question, right? It's we would propose an algorithm and say, okay, according to some the data that we've collected so far, we think this algorithm will work pretty well. We run it, we test it, we compare it, and we see, okay, is the data that we collect, does it is it more, I guess, refined? Does it? I don't want to say feel more right, but for lack of a better word, but does it match what we're observing?
That makes sense. For our CubeSat, I thought we're running our control algorithm loop in the OBC, right? We're
Yeah,
not running it in the ADCS.
yeah. So the Blue Canyon ADCS has its own algorithm built in, as it
Mhm.
should.
Right.
And Blue Canyon is not going to let us overwrite that data because
Oh,
yeah,
interesting.
yeah. So we can't like directly command it. Okay, here's a new algorithm. Go run that. No, we should
That's
not
what
do
I
that.
was gonna say. I was wondering, how could we put an algorithm into their computer so that our OPC doesn't have to be the one running it?
No, we cannot.
We can't. Okay.
Yeah.
That's
Remember,
unfortunate.
yeah, their product is designed to run their algorithms, and but it's going to run them like like spot
Hmm.
on, right, as advertised almost. Um, for us, the way that we would do it is the ADCS will have, I guess I'll put it as like a block, but the ADCS has, I guess, two modes you could say. You have mode one, where it's the ADCS controlling it itself. And then you have mode two, which is we will supply a command, right? We will say spin these wheels this much or generate this torque. Both of them will result in the same control of the four reaction wheels, right? But in this one, this would be generated by the OBC versus here it would be like internally calculated.
Okay, that makes sense.
Yeah, and we would be able to give a command like, hey, switch over from mode 1 to mode 2
Hmm.
from like the OBC or something. Yeah, from the OBC. But yeah. Um,
Okay,
yeah. So
that makes a lot of sense.
that's the estimation stuff. The next thing is the control algorithm. So this is what Mike is working on. I'll go a little bit into detail just because I know Mike focused on the research side, but I want to focus a little bit on more like just broad control algorithms. So the control algorithm is like what actually takes, a reference signal and it takes the reference algorithm or like no, sorry, not the what am I saying? Takes the reference, compares it to the estimate of where it thinks it is, and then outputs a command to, actually account for a change, you could say, right? You have your what's it called? Usually it's like so you have your reference coming in, you have your current estimate here. We'll say estimate. you take the difference of these two. This gives you your error. And then using this error, this is your control algorithm, CA. From here, you generate a torque that will correct it. This is the most vague sense, right? Usually this reference is like, either 4 quaternions or 3 angles. Your estimate is the same thing. You have to find a way to get the error. Usually it's not just a simple plus minus, but you'll get the error from these two values. And then your control algorithm will turn that into a torque, which 3 values, right? How much do you spin each wheel? And there are numerous ways to design these control algorithms. And I'm going to highlight a couple of them just so you guys have a good picture of what's possible and what's not, and what are the benefits of each one.
Mm-hmm.
So first you have optimal control theory. So this is, similar to the Kalman filter. You're asking the question of, okay, I have some reference and I have some estimate of where I currently am. What is the optimal torque that will take me there? And this is usually posed as like a linear quadratic Gaussian or LQG, LQR type of problem. And it's usually I'm going to minimize some function. I think it's xt. I forget what the I have to search it up because I don't actually know this stuff yet. I'm taking a class on it now.
We don't know what. Yeah, we don't know what that is either.
Yeah. I've learned this like very roughly in the sense, but yeah. Usually this is the matrix that you're trying to minimize, right? This Q, R, and N term. This Q is for, and the way this works is this is a cost function, right? You have some function that says, okay, if I take too much time, it costs a certain amount to take time, right?
Mm-hmm.
And then it also takes a cost on how much your control input you're using, right? If you could, if you had an infinitely powerful reaction wheel, technically you could do it in like a split second, but that's a ton of electricity that you have to pump in for like a very small amount of time. So there's a cost to using, a large reaction wheel in terms of energy. And then there's like a cross-coupling term, which is, the amount of, where you are plus, how much energy it's taking. And what the linear quadratic regulator does is it optimizes this, or rather it minimizes this. And there's a lot of math on how to solve it, which I will cover later on in this semester. But the end result is, you get this K matrix that tells you, okay, this is your optimal solution according to what you defined as the cost function.
Is this the kind of math that's going to be done on the ground?
Yes.
To create? So when you talk about this algorithm, this is the algorithm that we could use to train a machine learning model.
No.
No. Okay.
No, we don't use this to train anything. This is like, so optimal control is usually just like, it's like the go-to almost, right? PID is a form of, well, it's not actually a form of optimal control, but PID and optimal control are they're not too far from each other on the map of control theory. So optimal control is usually used when, you're just trying to find, okay, what's the optimal solution according to these constraints that I've put forward, right? That's it. It does not account for things that are crazy. And another important thing, optimal control theory, at least this one right here, this linear quadratic regulator, only works for a linear system.
Right.
We do not have a linear system. Matter of fact, I don't think anyone does. So it works in certain places where the linear assumption is valid. It will most likely not work for us. We will use it to test it, like, okay, like, just this is what the optimal control solution is according to, what we predict from just hand calculations or maybe a simulation. Here we ran it, and this is how it deviated, and this is, we can see like this is the effect of the nonlinear terms in our dynamics, which would be the fluid slosh. So yeah, that's optimal control. Usually you're trying to optimize some cost function. Then you have what's called robust control. So this is more along the lines of what we would try to use. So same idea, but now instead of trying to be optimal, we're trying to be safe, you could say, right? We're trying to be robust to uncertainty. If you want to think of this in terms of like an ODE, rather so you guys know that there's like for a step function there's an optimal solution, which is like the critically damped solution, right?
Yeah.
But here's an interesting way to think about it. That critically damped function,
We just learned this in differential equations.
yeah, and yeah, I'm about to ruin it. I'm about to ruin it for you. But here's a thought, right? When you find the critically damped solution, that assumes that you know m, c, and k to infinite precision, right? If imagine if k was bigger by 0.01, now you're no longer critically damped. Now you'd be somewhere either in the, what am I saying? The overdamped case or the underdamped case. You are no longer critically damped, right? And so what robust control does is it says, okay, I'm going to take an approach that is guaranteed, like, okay, let's say I have plus or minus 1% here, plus or minus 2% here, plus or minus 0.5% here. I'm going to take an approach that no matter what will always meet certain requirements. Does that make sense?
Okay. Yeah, that makes sense.
So even if this was like the worst case scenario, this solution would never end up shooting past if that was like a constraint that you wanted to place. Right? And so in the face of these uncertainties, the controller is designed to account for them. Or rather, it's designed to account for the worst case scenario.
That makes a lot of sense.
Yeah. So that's...
Whereas optimal will go for like...
So
it will go for an ideal thing where like...
Yes.
Yeah.
Yes. So this accounts for model uncertainty. Let's see what the next one is. Adaptive control. Okay. Adaptive control, I think it was the Wikipedia page that mentioned this, and I think I really like this. I don't know how true it is, but I'm going to hope it is true. Adaptive control adaptive control is when you are learning how to control your system by controlling your system. So this sounds very weird, but imagine if you put a computer in a car, right? And you said, okay, I want to drive at 60 miles per hour. If you don't tell the computer anything, it has no idea what to do, right? But if you loaded something that was, like an adaptive control algorithm on it, it would learn how to drive by driving, right? It would put in an input U, and it would get some measured output Y. Based on that, it would modify its driving, right? So you're kind of learning how to drive as you drive. Not the most ideal, but it does work in some cases, right? I wouldn't even say some. It has worked in some, in these cases it does work. Yeah. I don't know too much about it, but I do know that it exists. And I know it can be very good or very bad, because imagine learning how to drive a car for the first time, and that's how you were taught is, here's the floor pedals, good luck, buddy.
Yeah, really. That's kind of scary.
Yeah. When it does work, it works very well. When it doesn't work, it can go very poorly. So, I guess this is learning... No, not learning while. Learning by doing. That's the way I would put it. Don't know how accurate that is. Let's see. The next one is intelligent control. So this is actually what Mike does. Intelligent control...
This is machine learning.
Yes, this one's machine learning
Okay.
and neural networks, AI, all that fun stuff. Yeah. So
Yeah, that's my bad earlier. I saw the word cost function and my brain just immediately went, oh, cost function, machine learning. It must be.
yeah, no, not for optimal, but for intelligent, there's always a cost function, because when you do machine learning, there's usually some way of training the machine learning algorithm. It's usually a cost function. But what machine learning and AI hopes to do is, by using those that data, right? By using the data to train, by using the the massive amount of data processing that happens, you're able to account for things so long as they fall within certain criteria, right? And Mike mentioned this, so I'm not gonna go steal his thunder, but the main part of our mission is the amount of data we're collecting, right? We are downlinking a ton of data. We're downlinking pressure data, video data, motion sensors, attitude data. We're downlinking all of that. and that can be used to train something, and that something is going to be a lot smarter than anything that we can do on, like, just by like a simple equation, right? I say simple in a loose sense here. So yeah, intelligent control, fun stuff. I do not understand it. But one important thing for machine learning is, and this is something we realized very recently, so, which is it takes a lot of processing to do, right? Spencer, you did this just a few days ago, but when we covered the, how much multiplication the CPU would need to do, like it was like something like 17,000 multiplications at like, I don't know, whatever speed the control loop is running at, right?
Oh yeah. But that was assuming, for that we assumed it was a linear control algorithm.
Yeah.
Right.
Usually linear is worse than, or sorry, not worse. It's usually more computationally intensive than nonlinear. Nonlinear
really?
control. Yeah, nonlinear control. I can get into this. Actually, it is the next thing, so I will get into it. But yeah, it's the next. Yeah, it's not there, but I'll do it anyway. So the benefit of nonlinear control, and my professor, if she sees this video, she's going to scream at me because I know she taught me more, but I can't mention all of it now. What nonlinear control does is it essentially tries to find like a perfect, not a perfect, but it finds a function that is guaranteed to bring the system to equilibrium. So here's a thought. Oh, I didn't mean to scroll down. No, go back. Okay. So let's say you have some nonlinear function, x dot is equal to f, x and u, right? This u is designed so that the energy of the system, which is this v, always goes towards zero.
Okay.
Now, if the energy goes to zero, or sorry, not the energy goes to zero, it's more like the energy is always decreasing. So the derivative of the energy is always less than zero. Well, a strong condition is it's less than zero. Weaker condition is that it's less than or equal to zero. What does this mean? This means that no matter what happens, the system will always tend to lose energy, which means it's converging to a point. By being a little careful with this u and the function that guides it, you can make it converge anywhere. But
Okay.
this is a lot simpler in the sense of you're just taking the energy of the system and bringing it down constantly until you hit an equilibrium point, right? That's a lot simpler to do than, like, as you saw, like a 91 by 91 matrix multiplication, right? This is usually what this is it's like it's a scalar function, right? You say, I'm going to take some simple, I can't do it right now because there's a lot of math, but if you're interested, look up Lyapunov functions. The idea is
What function?
Can you spell that?
Lyapunov.
Oh, yeah. What the?
Lyapunov. Interesting.
Lyapunov function. I feel like there's going to be a graph that explains it. Yeah, it's like this. Basically, your system will draw.
Gradient descent.
Yes. Not gradient descent. That's
Not gradient descent.
That specific term is reserved for something in machine learning, or I guess machine learning, AI, and all that fun stuff. But the idea is that if your control system with the control input is always decreasing in energy, then you will converge to this point. In this case, it happens to be 0, 0, right? But here's what you notice. The slope here is always negative, no matter where you are. Which means no matter where your starting point is, if you apply this control, right, your total system energy will converge to 0, which means your system is slowly coming to like a halt, right? And the functions for this are, they're a little more crazy, right? This is crazy. Let me see if I can find a control example, but no, this looks terrifying. This looks like my homework, actually. This looks a lot like my homework, actually, this nightmare material. But, the idea is that the actual function is a lot simpler. This is a very simple function right here compared to, like, a large matrix problem. It's just, what's the current energy? Slowly bring it to 0. That's it. And that doesn't take as much multiplication as, matrix multiplication would.
Right.
So yeah, that's nonlinear control. Fun stuff. I have learned it, but not very well yet. I still need to review for my exam. Yeah.
What's the benefit of linear control?
Linear control? All the
Yeah.
math is easy to work out.
Okay.
Or rather, linear control is you can apply superposition. That's the benefit, right? If you have one solution and you have another solution, you can add those two and get another solution. That is
Uh,
yeah, that is
I see.
invaluable in terms of
Mhm.
designing things, right? Imagine if everywhere 1 plus 1 was 2. But you know, for nonlinear control, the benefit is the system is more. It's usually easier to implement, right?
Mhm.
People were implementing nonlinear control using op amps. It's really hard to do linear control with op amps, right? You can make like a single PID loop, but usually no more. For a
Mhm.
nonlinear system, you could, in a very loose sense, you could literally hook up the output of a sensor to the actuators, and then assuming you have the right stuff in between, it would work, and it would work
Yeah.
very fast, and it would in fact converge to zero if you had designed it properly.
Mhm.
So yeah, the benefit of nonlinear is it's when it works, it'll work very well, and it'll do it with like the bare minimum of like
Mhm.
computational cost and with a ton of speed. The problem is it's usually a lot harder to develop. Matter of
Okay.
fact, this is actually Berlion's area of research is nonlinear control.
Okay.
So yeah, if you're interested, go look at some of his papers. He does a lot of stuff, and it's very crazy. So yeah, these are
Ooh, take
the
a look.
yeah. So these are the main control laws that are used. There's more, but I don't have them fully understood yet. I'll learn them
Mhm.
eventually. And by eventually, I mean this semester and over the summer. So, yeah, that's this. Now, do you guys have any questions and the related?
Um, so far, no.
Damn.
We usually ask like during, yeah.
Yeah.
Okay, yeah.
We will interrupt you with our questions. Don't worry.
Nice. Um, let's see. Okay, well, if that's done, then I'm going to go on to the pointing budget because that's something that Spencer, you're gonna have to do when I leave. Well, you're gonna have to help me with it at least, even
Yep.
if I'm in this club. um,
Okay.
so the pointing budget is essentially something that quantifies how much pointing knowledge and pointing accuracy we can have based on the requirements of the mission, right? So every component that I've talked about will have errors, right? Your star
Mhm.
tracker, it runs very slowly. Um, your IMUs, they're prone to drifting. I'm gonna call this the OBC. Your OBC will have a time delay attached to it, right? It's gonna take time to process the data and give you the value out. There's gonna be some error in there. When you relay this to the reaction wheels are not perfectly balanced, right? There's going to be some error in them. There's another time, or not time delay. There's a model uncertainty there, right? The reaction wheels may have jitter. That's a possibility.
Mhm.
All of these things are part of the will contribute to error in pointing, right? You say you want to point at exactly, say, I don't know, 0 degrees, right? So you're trying to point exactly at 0 degrees, whatever that means. And this is like the two-dimensional case. Your actual pointing would be like within a bound of sorts. And you would say it's like plus or minus some small amount e. For our mission, we want to minimize e as much as possible. And in here, there's actually two of them. There's e in the pointing, and then there's e in the knowledge. So, there's going to be some error associated with. I shouldn't make these the same color. I'm going to make these different colors.
Hmm.
I'm going to say, yeah, this one. So this is going to be the E knowledge. Um, Usually, your pointing knowledge is a lot better than your pointing accuracy. If you want to understand why, I would think about it like this. You can only know how accurately you're pointing if you know where you're pointing. Does that make sense? Like, it's a bit weird when you say it out loud like that, but you know, you can only point as accurately as you can determine where you are pointing. So
Yeah, that makes more sense. When,
Yeah.
when you say it like that, that makes a lot of sense.
Okay, yeah. So usually the pointing knowledge is, which is part of like the attitude determination, is a lot smaller than the pointing errors, but they do both matter, right? Because we're trying to do both as accurately as possible within the constraint of our budget. So, you know, the pointing errors are the errors that come from, you know, how do you determine your attitude, and then how do you process the data fast enough. Whereas these are the determination errors. I used the wrong color. Whatever. Yeah, your determination errors. Oh, I cannot do this. Okay. Yeah, your determination errors usually come from like your OBC, no, not your OBC, your star tracker inaccuracy, your IMU inaccuracy, how good your filtering algorithms are, how slow your OBC is, right? What's the time delay between these? These right here are all the sources for your pointing knowledge error.
Mm-hmm.
For your for pointing determination, right? Attitude determination is dependent on the sensors. Your attitude pointing depends on your actuators as well, right? So there's like one extra layer of errors here. So usually your pointing error is going to be greater than your determination error. Does that make sense?
That makes sense, yeah.
That makes sense.
What's error on top of error?
Yes, exactly. Yeah.
Is there a certain allowable error that we have been given for communication?
So I don't want to give you an answer because we recently got the PDR feedback, and they said I did it wrong. So, so
It's okay that there's room for improvement.
yes,
Okay.
yes, there is room for improvement. Yeah, I unfortunately, you know, I had to write that document without much knowledge on, you know, ADCS. I am still not the ADCS engineer. That's happening over the summer / later this semester. So
Yeah, and Blue Canyon hasn't given us the
Yeah.
specs yet. So yeah.
So, you know,
That's
that document had a lot of errors. I do have to go back and fix it, so I will. But it's important for you to know, you know, what this document is, why it's important, and what exactly it's asking for. Because you two are going to be helping me. At least you, Spencer, definitely.
Okay.
So, yeah. Usually when you have like, and I guess I mentioned this very faintly, but you know, when you have an antenna, there is there's a radiation pattern, which determines the intensity of the signal that's being sent. So, let's say your antenna is like this, right? It's a patch antenna. Usually, the largest signal will be like right in front of it. I drew that terribly. It'll be like right in front of it, and then there'll be like these little bulges sticking out the sides.
Right, and that depends on the gain of our antenna, right?
Yeah, this depends not just the gain. This just there's a ton of antenna features in here, which Shri will mention when we have the communications podcast. But this radiation pattern, you know, this one bulge is the main bulb, right? And this is what you would want to point at a ground station. And I think the word they use is like half power beam width, or some variation of that, which says what is the angle that will have half the power of this. And that angle is usually what you use when you say, okay, I need to point my antenna better than this because I need at least half my power to be going to the ground station. So, yeah. This is like this is related to the communications requirements. I'm not going to go into it because I don't understand them very well, but I know
No,
that.
that's okay.
Yeah.
I for the communications, I did some of my own research and I looked up like stuff about gain and like
Yeah.
other things for antenna, and I found a bunch of horrendous equations that just looked so ugly.
Yeah.
So it's okay.
Yeah, no worries. Shree will explain it to you in the next, I think next episode or after that. I think something. Yeah. So, yeah, this is what the pointing budget is. Usually this data is provided in data sheets, which yeah, well, Blue Canyon, please, if you're listening, send us your data sheets already. But there are things that we can currently define, right? If we know what the antenna is, and we have the document from there, or like the document on their radiation pattern, we can get the half power beam width angle from there. If we have any other requirements like charging, probably don't, but if we do, then that's another one.
Mhm.
For us, the majority of the requirements come from the payload side, right?
Right.
The ability to accurately determine your attitude and pointing is very important for this mission, right? The
Mhm.
better you know your attitude determination, the better you can see those little fluctuations because of the sloshing disturbance. The better we can account for it through the reaction wheels, the better our mission is going, right? Like
Right.
that's what like a successful mission would be. Like a fully successful mission is we're able to do all of these things and we're able to make an actual impact via the controllers that we develop and the data that we collect.
That makes sense.
Yeah.
Yeah, I think we're trying to remove the need to sun point. I think we're trying to have solar panels on all the faces except for the side with the camera, with the antenna.
Yeah, yeah,
So
that's
we
fair.
don't have to worry about that.
Mm-hmm. Let's see. Yeah, I think that's all for me. I
Okay.
I have a lot to
Um,
learn about the ADCS still. I have a lot to learn, but I'm learning slowly.
Okay, that's fair.
I think I learned a lot.
Yeah, me too.
Take take
I
everything
was
I said with a grain of salt because do your
Yeah,
own
of
research.
course.
I'm gonna do my own research anyway. Don't worry.
Yeah.
That's not because of you. I would have done that anyway.
But yeah.
Nerd.
All right.
A question I had real quick is it's important for us to determine our pointing, while we're communicating, right? While we're pointing at the ground station.
Mm-hmm.
Um, while we're doing that, how does the star tracker work if the star tracker is also pointed at the Earth?
Ah, I'm so glad you asked. That's actually a problem that we have to go through
Okay.
because the more pressing concern, which what I thought was a pressing concern was if we do our experiment and the sun happens to be in the way, would that affect the
Mhm.
star tracker, right? And
Right.
not Blue Canyon. The UNP said I don't have to care as much, but I do think I'm gonna think about it.
Mhm.
Regarding the Earth case, the simplest solution would be to have two star trackers pointing out opposite ways, so at least one of them is looking at the night sky.
Right, but then the payload's on the other side.
Yeah,
So
exactly.
yeah, that's tricky.
So yeah. So I guess for us, it would be something like we would have to have one star tracker pointing out this way, one of them pointing out this way,
Right.
and that would be very annoying. I think
Mhm.
the way we can try to get around that would be designing our what's it called, our experiments to try and be more inclined towards okay, the Earth is here. Do your experiments in this half of the sky. You know, always
Uh-huh.
try to keep your star trackers pointed away from the Earth. If that doesn't work, you know, we can always use IMU data to try and make up for a poor star track or not like an unusable star tracker.
Mhm.
I think it's also possible to use a horizon sensor. So a horizon sensor tells you where the horizon of the Earth is.
Right.
So if you are able to use that properly, then it is possible to, like, you know, if you do like a little bit of a sweep, you can account for it. It would be a problem if like the final angle was like, okay, point straight at the Earth. Like, come on, that would be a bit annoying. But
Right. And if we're communicating with the ground station, then we will be pointing straight at the Earth.
yes. So
okay.
so this is where like a little bit of the configuration thinking has to happen. So if the star tracker is pointing out this way, we would want our antenna to be this way.
Okay.
That way, even if this is pointing straight at the Earth, or I guess I'll rotate this picture a little bit to make my own life easier. Even if we're pointing our spacecraft like straight at a ground station, at least the star tracker has access to space.
Okay, I think I'm gonna bring this up with the structures team because I think right now they're pointing in the same direction.
You love to see it.
So it would be good to not have that happen.
Yeah. Hope. My goal is by the end of the pod. I'm kind of glad that you thought of this on your own, because I think that's important. I have, like, I had an answer. Like, obviously, I knew this ahead of time, but I don't think if I mentioned it, it was very like brief. I was like, hey, by the way, if you need help with designing the insides, let me know. But they never messaged me. But now that you know,
Right.
that's pretty good, actually. I would say that's a really good sign if you're able to think of this on your own. Hell yeah.
Yay.
I'm training you right. You're being trained right. We're winning at life. Yeah. Considerations everywhere. Systems engineering. Welcome to systems engineering. This is your job.
Building the systems and engineering.
Yeah. You get to keep track of everyone's work.
They're separate.
Alright, well, I think that's all. Do you guys have any more comments, closing concerns? This isn't a role that exists yet, but it will sooner or later.
I think it's really
No, I
good.
think that was pretty good. I think we're good.
Alright then. I'm gonna end the recording in 3, 2, 1.